Good morning, everyone. I'm glad to make the presentation of generative tensor network classification for supervised learning. I'm Zheng-Zhi from University of Chinese Academy of Science. Our work is mainly about classifying images in quantum space. I will introduce it to you from two aspects, which includes how images distributed in quantum space and the performance of a mode. Here are some preliminaries about classifying images in quantum space, which contain two steps. The first step is to map images to is to map images to the many-body Hilbert space or quantum space. This can be easily done since we can map one pixel. Since we can map one pixel to a vector, which is a wave function of one single spin. For example, we can map a blank pixel 0 to a spin up. By this way, each image can be mapped to a product state. The next step is to calculating the distance between the product states and the metro product states representing entanglement state supposed by training set images. Then the classification can be made by comparing probabilities of images having different labels. The probability is defined as the square of fidelity. Now let me introduce how images distributed in quantum space. One may ask why bother to map images to quantum space? As shown in this figure, it may occur that in the classical space, an image of black cat may be close to an image of black bear, while we hope that in quantum space, an image of black cat is close to an orange cat. Well, this is a conjecture, and we should test whether it is true. This figure shows the average including distance and fidelities between the samples of a mixed data set in the original and quantum space. In this figure, the dialog terms represent for the average distance of images with same label, and the non-dialog term represent for the average distance of images with different labels. We can easily see in the quantum space, the dialog term is much larger than the non-dialog terms. This indicates that it will be much easier to classify images in quantum space. Now let me introduce the performance of a mode. Firstly, here I will give a brief introduction about the tensor network representation for an entangled state. As I have mentioned before, the classification is made by calculating distance between the product state and the entangled state, which is superposed by a lot of training set images. The coefficient matrix of this entanglement state can be written as a large tensor. Then the training process is to optimize the metro product state to approximately represent this large tensor. We should note that the metro product state has a much lower entanglement entropy than this large tensor. Now let's compare the performance between our mode, GTNC, and the supervector machine. These two methods share the same idea of mapping images to a higher dimensional space and classify them by hyperplane. After turning several sets of hyperparameters, the best performance of SVM is still lower than GTNC. This indicates two things. The mapping of GTNC is good, and the classification hyperplane obtained by GTNC is good. A more interesting result occurs when we compare the performance between GTNC and baseline mode 1. Baseline mode 1 makes no appropriation to the coefficient matrix of the entangled state. This means it can correctly classify any image in the training set, while its performance on the testing dataset is not as good. We conjecture this is because metrical product state has a lower entanglement entropy than the large tensor. In other words, we think the entanglement entropy may contribute to solving overfitting problem. I will summarize our contributions into 2 points. The first point is that images with same label are closer in quantum space. The second one is that generative tensor network can obtain a good classification hyperplane in quantum space. Okay, thank you.